Particle physics, neutrinos. So for example, we're going to have a look at the 2015 question 10a. And it's important to note, obviously, the particle physics is a higher level option only, so you would never find this on an ordinary level paper. And as it stands, everybody in the class is doing higher level at the moment. But if for some reason you are changing to ordinary level, then you do not need to study particle physics. Same way you don't need to do the circular motion and simple harmonic motion. They are only higher level also. We're not going to do all of this question because we haven't done some of the theory behind it yet, but you can revisit it after the chapter is finished. So what we want to have a look at here is the first part of the question. We're told there's about 1 trillion neutrinos from the sun passing through your hand every second, and it's not subject to what's known as the strong nuclear force because it is a member of the lepton family. Now again, we'll come back to those particle families at the end of the chapter. And also we'll look at the fundamental forces that are impacting on particles. So we won't be answering this part of the question here. So you can just star that for later. However, we're going to look at the first part of the question. So I'm just going to number it 1. And we're told Pauli proposed that a neutrino is emitted during beta decay. So why did he make that proposal? So I'll get you to pause the video and then see, can you write down the answer based on what you heard earlier? So of course he made that proposal because he was saying in beta decay, he noticed that momentum and energy were not conserved. And of course, we know that we have to have conservation of momentum, conservation of energy, and conservation of charge in any of our nuclear reactions. So they were not conserved in beta decay, and therefore that's where his proposal came from. So in the next part of the question, it says, during beta decay, a neutron decays with the emission of a proton, an electron, and a neutrino. And we have to write a nuclear equation to represent this beta decay. So again, we'll number 2, and you're going to pause the video and see, could you come up with this equation? I haven't shown it to you yet. So see, can you predict what the equation is going to look like? Okay, so what you should notice there is that it's a neutron is decaying, right? So we have to have a neutron, and it is decaying. So therefore we have our arrow showing our decay. And we're told it's decaying into a proton. So you can either do P for proton or you can do H for the nucleus of hydrogen. And we have an electron and a neutrino. Okay, now the symbol for a neutrino is the Greek mu. That looks a bit more like gamma, so let me do that properly. That's a bit better. So nu is the symbol for the neutrino. So it's like a little kind of fancy V. So again, you can go to the back of your books. And in the back of your books on page 401, you can see all your Greek alphabet there. So nu is the small lowercase symbol that you're using for that. Okay, so here's our equation, but this isn't fully right. We're not going to get full marks for this because, of course, we're missing all of our atomic mass numbers and our atomic numbers and our mass numbers. So, of course, the neutron should be 1, 0. Our proton nucleus is 1, 1. So again, as I said, that could be H1, 1 either for that, okay? And then we have the emission of the electron, which is 0, minus 1. And then the neutrino. And of course, the neutrino has no charge. That's why it's called the neutrino in the first place. So there's no charge, and it's basically very, very little mass altogether. So you would be getting 10 marks in total for this. So again, you have 2, 4, 6 for all of your numbers there. And then you have your 4 symbols, N, P, E, and nu, to get the other 4 marks. So it's basically 1 mark for each part of that equation. And generally that's how it works for all of these questions. When you're asked to write out a nuclear equation, that you're kind of getting 1 for everything there. And that was 4 for that. Okay. Now, the next thing it says is we then have to go on and calculate the energy released during this beta decay. So to get the energy released in beta decay, we know we're going to be using E equals mc squared, where the m is the change in mass. So in other words, the mass before minus the mass afterwards. So before we can use E equals mc squared, we're going to have to work out this loss in mass first. So if we look at the question from 2015, there was no numbers given in the bottom of the question in brackets. So often we're given hints to masses or what to take the speed of light or gravity in brackets underneath this question. But in 2015, they didn't actually do that. So we were totally reliant on knowing where to go in our maths tables. So every time I'm saying it's really important to know where everything is in our maths tables, it's for situations like this. So what we had to do then is to work out our change in mass, we need to look at before and afterwards. In other words, we need to know the mass of the neutron, the mass of the proton, and the mass of the electron, where the mass of the neutrino is very, very small and negligible in this situation for this calculation. So we're going to go to page 47 in our maths tables and also page 46 to work out the masses. So if we look at beforehand, well, our mass is the mass of the neutron. And we can see that the mass of the neutron is page 46. And in particle physics or modern physics, we always, if we're not given the values, I would take literally every digit that is given to us on these pages to be as accurate as possible. So we have 1.674922728 by 10 to the minus 27 kilograms. And then we need to look at the mass after. So our mass after is the mass of the proton, which again is on page 47 this time. And we can see that's 1.672662171 by 10 to the minus 27 kilograms. And then we also have the mass of the electron. And the mass of the electron is page 46. So that's 9.1093826 by 10 to the minus 31. So much smaller than the mass of the proton, and the mass of the neutron, you can see, are very, very similar. Okay, so if we get the mass of those two together, so we add those, that gives us a mass of 1.67353264.8 by 10 to the power of minus 27 kilograms. Okay, so we have our mass before and our mass afterwards. In Einstein's equation, we're looking for the loss in mass, so the mass defect. So therefore, we need to get the difference between the two of these. So we say delta M then is going to be 1.674922728 by 10 to the power of minus 27. And that's minus 1.673532648 by 10 to the power of minus 27. And therefore our loss in mass is 1.394632 by 10 to the power of minus 30 kilograms. Okay, so now we have our loss in mass. All we need to do next is work out our energy. So we'll go on to the next page for that. So therefore we have our energy is going to be our loss in mass, 394632 by 10 to the minus 30, by the speed of light squared. Now again, speed of light wasn't given to us in the question, so I'm going to use the speed of light that's in my maths tables based on that's what I have to go on, which is page 47. So normally we'd say 3 by 10 to the power of 8, and of course that will still give you the same answer, but no values were given, so I'm going to use what's in my tables. So that's 9, 2, 4, 5, 8, and that's by 10 to the power of 8. And again, be careful, you're squaring your speed of light here. So therefore that will give us our energy, and it's the energy released, which is 1.2534326 0.732, and that's by 10 to the power of minus 13, and that's in joules. Now, if we look back at the question here, we have to be very careful because it says find the energy released, which we've just done, but it has to be in mega electron volts. Now, in mega electron volts, well, first of all, we need to worry about changing it to electron volts. So again, to change it to electron volts, we divide by the charge on the electron. So again, if we go to page 46, 1.253432732 10 to the minus 13. And on page 46, you'll see the electron volt. Okay, so in other words, we're dividing by 1.60217653, and that's by 10 to the minus 19 joules. So in other words, when I divide one by the other, I'm now dividing by the charge in the electron, which will give me my energy in electron volts. So that gives me a value of 782,331.2282. Now that's in electron volts, but the question clearly stated, again, let's go back to it. It didn't say electron volts, so I still wouldn't get my full marks here. It has to be mega electron volts. So really important that we are underlining our key words there. So using those highlighters, okay? So to get it in mega electron volts, well, mega, again, if you can't remember your prefixes, well, what page are your prefixes on? They're on page 45 in your tables, and mega is 10 to the power of 6. So of course, if I divide by power of 6, I'm moving my decimal place back. Well, you can see I end up with 0.78233122282, or just 0.78 will do, mega electron volts. Okay, so for that question, we were getting 3 marks for our mega electron volts. We were getting 3 marks for our energy in, up here, our energy in joules. We were getting 3 marks for our formula, which was our MC squared up here. And we were getting 3 marks for working out our loss in mass, which was this value here. So in other words, we had a total of 12 marks for that calculation. Okay, so the fourth thing we want to look at here is an electron can be detected in a cloud chamber. Now, we haven't discussed what a cloud chamber is yet, okay, but it's a means of detecting particles. But what I'm interested in is, however, it is much more difficult to detect a neutrino. So why is it difficult to detect the neutrino? Well, we saw already with Cowan and Rains, they had to have this huge tank of water, and it had to be distilled water. In the Super Kamiokande in Japan, has to be a huge tank of distilled water. It has to be deep underground. If we're looking at the ice cube, the neutrino detector in the Antarctica, it has to be, again, deep down, dug into the ice, where we have no cosmic rays, no background radiation interfering with these photomultiplier tubes. And therefore, the reason it's so hard to detect is because it basically has no charge, first of all, right? So therefore, it's not going to be affected by any electric fields. It's not going to be affected by magnetic fields because it has no charge. So that's really hard. It also has a very, very small mass, which makes it really, really hard to detect, because it's going to very weakly interact with matter. And also, if it has no charge, it doesn't cause any ionization. Okay, then if it doesn't cause ionization, then again, it makes it hard to detect. Okay, so there was 6 marks for giving one of those answers. So one reason, and you were getting it. Okay, so I would probably give a couple of reasons, but again, if you can remember 1 or 2, then that's really, really going to help in your explanation for why do we find it so hard to detect our neutrinos. Okay, now the next bit is a calculation. That's a nice little calculation on circular motion there, actually. But again, we can come back to the... Actually, no, do you know what? We may as well do that one now. Okay. So there's a good bit of revision on your circular motion, which was just finished last week also. So we have a cloud chamber basically detects an electron, and when the electron enters the cloud chamber, what happens is you end up with this trail in the cloud chamber. And what happens is if we apply a magnetic field to this cloud chamber, then you'll see the trail moving in a circular motion. In other words, we see that it'll move either to the left or the right, depending on the charge on the particle. So here we can see that we're given the radius of the circle that is left behind in the trail caused by this electron, and we're asked to calculate the radius of the circle. Now we're given the magnetic field, okay, magnetic flux density, and we're also given the speed. So if we think about our circular motion, let me call this 5, then what we have is the force felt by a charged particle as it enters a magnetic field is given by BeV, right? So in other words, our magnetic flux density by the charge on the electron by the velocity of the particle, or the speed of the particle. I'll just make that V smaller just so you're not getting confused with... potential difference there. But if it's moving in a circle, we also know that it's going to experience centripetal force because it's circular motion. So because it's linear speed, it's going to be mv squared over r, and not our angular velocity. So of course, both of these are representing the force on the electron in the cloud chamber. So we can equate both of these, which gives us mv squared over r is equal to BeV. We can see that one of our velocities is going to cancel there. And if I multiply both sides across by r, and then divide across by BE, well, we can get the radius of the path of the electron. So all we need to do then is list out our values. So do we know the mass of the electron in the question? No, we're not told that, but we do know that if we go to, again, page 46, that we can get the mass of our electron, we said, was 9.1093826 by 10 to the minus 31, and that's kilograms. With the speed we're given in the question is 1.45 by 10 to the power of 8 meters per second. The magnetic flux density, we're told, is 90 milliteslas. Now, of course, milli, if we go to page 45 in our maths tables, is 10 to the minus 3. So that's going to be 90 by 10 to the minus 3 Tesla. And then E is the charge on our electron. And again, charge on our electron is on page 46. So that's 1.6027653 by 10 to the power of minus 19 coulombs. So if we sub all of those values into our equation there, then what we end up with is M, so 9.109 minus 31 times the speed, which is 1.45 by 10 to the power of 8, all over flux density, so 90 by 10 to the power of minus 3, and then charge 1.6021763. And if we put that into our calculators, then we end up with 0.009160181, or in other words, 9.16 by 10 to the power of minus 3, and that is in meters. So again, we were getting 3 marks for working out our radius, 3 marks for actually equating those two equations, and 3 marks for identifying one or both of the actual formulas. So by writing down our forces, we were getting 3 marks. By equating the two forces, we were getting 3 marks. And then for the calculation itself and getting the answer out in full, we were getting 3 marks. Okay, so if I go back to the last part then of the question, we're asked to describe the neutrino's path in the same magnetic field. Well, if I'm looking at the neutrino's path in the electric field, well, clearly there is no deflection, right? So in other words, there is no deviation of the neutrino in any magnetic field, in a magnetic or electric field for that matter, because obviously it has no charge. Okay, so there was 3 marks for that part, right? So nice question there, mainly focusing around the neutrino and obviously the fundamental forces of nature there at the start, and the lepton family. We'll come back to that at the end of the chapter, which was 12 marks. Okay, so I'm not giving you any calculations or work to do today. It's more so about just actually going through this whole exam question yourself and having a look at it, and maybe even having a little look at Conan Rain's video or something like that. But really it's kind of the background theory and going through the equation there for your beta decay. Really, really important to know that off by heart. So big fat NB next to that equation there. But again, if you're going through your physics checklist that I highlighted there the other day in the video, all those nuclear reaction equations are in that handout as well, highlighting to you the ones that you need to know off by heart. Okay.